So I'm going to have to rush through the first few bits because it's a lot of theory. Yeah. So I work in incident response. I'm basically a blue teamer. I do like a bit of red teaming, but most of my work is coding, automation, and stuff. I've been associated with my local DEF CON chapter, but this is my first time at B-Sites. And let's see how it goes. So P files, for some background. These are compile files. They cannot be read as is. They encode all the functions and so on. The ancestors include MS-DOS, exe with the MZ, which is pretty common. And it was originally meant to be 32-bit. It was supposed to be a container for .NET assemblies because that's what Microsoft preferred. And then over time, it's evolved, to be more generic, include 64 bits. And of particular note is dynamic link libraries because we'll be using that. These include the abstracted functions. And unlike typical Ps, which are meant to be the base for your processes, DLLs are going to be your centralized repo of functions, which your multiple processes can rely on to reuse code. Yep. And just a high-level overview, basic sections would be a DOS header, a PE header, and several sections. DOS header is just for compatibility. PE header defines the metadata, and the sections, which we'll get to in just a second, kind of looks like this. The DOS header, your various headers, and then these basically compartmentalize your data, your raw data, which is included in the PE, and divides them into meaningful sections. For example, the .text would include the code for your program. Your data and our data would include your global variables, static variables, and so on. A process, it's an instance of a program, and of particular note is a structure called eProcess within the kernel, and it represents everything that's related to a process, its structure, its attribute, and so on. And when a process comes, to be born, it gets a PID, which is an integer value, or it's called a handle. And it uses the PE file to build a structure and define which tasks it needs to be executed on. So, and the PEB is a substructure within that, to which the E process points to, and it holds the heap manager and lots of associated stuff. So if you look at it like this, this is the memory mapping of a process, and you can see the PE there in like the fourth line, and the rest is stuff like your stack, heap, your various DLLs, and so on. RWX-S binaries, and this is what I'm here to talk about. So typically, I just mentioned about the compartmentalization using section headers. They define how a section of memory would behave when they're mapped to a process. And typically, they're supposed to be readable, executable, and writable. But I'm going to be talking today about something called shareable, or S. And these are defined by the top 4 bits of the characteristics property. The characteristics, if you'd like to see here, is 4 bytes, 32 bits. And if you see there at the very corner, you'd see is executable, is writable, shareable, and so on. So if just 2 of them are set, it's just these 2 bits here. That'll be 4 plus 2, 6. And if all of them are set, it becomes F, which is shown by the blocks in blue. Yeah. And this is what happens when you turn that bit on. This is my malicious process. That's a notepad. Both of them are loading the AMC DLL, common DLL. And you can see they both load at the very same memory address, ending in 4 zeros. Now, this is not a relatively new concept. It's been in research since at least 2004. But of particular note is a research by someone called Bill, who actually hunted for this using VT's retrohunt functionality to find a lot of existing DLLs which can be abused to leverage this function. Sorry for running through all that. Let's go a bit slower now. Now, I built a little tool to bring this concept into the real world. It's written in C#. I wrote it in .NET 6 for long-term support. And a lot of the base coding is passing it from unmanaged code or raw binary data. So I had to use pinvoke. And it's supposed to be good with loosely coupled and highly cohesive. But yeah, 64-bit as well. So just a quick run through of how the menu looks, which I spent an insane amount of time more than the coding. The target DLL, you just put in your path. You have it written right there. And you get a set of options to select which particular section you want to modify, whether you want to change it, whether to even add a whole new section if you'd like. And once you select your DLL, you get to choose which section you want. As if you remember, this just has 6, which means it's just 2 bits being set. And if all was set, it would have been F, and that's going to be our final name. So once you select the section to modify, it will modify it and create a copy of that DLL within a subfolder right there. And that will be automatically loaded into the program as well. So once you do that, you have the option to load it into the process in order to manipulate memory. And then when you check the sections again, you can see the one that was 6 earlier changes to F, meaning we've essentially made that section into a shareable section. And this is me selecting it again. And once you do that, you can select a payload as well. Now, a payload is usually your shellcode, which you use with any typical injection sort of engagement. And you can select either the starting address of that full section or even a specific function. Now, those who are familiar with export address tables would know if you have a code block, it would export a whole list of functions. You can specifically target a single function within it to give you more fine-grained control. We'll get to that in a demo towards the end. So once you've set all that and you've finalized on what you want to target, you select a payload within the attack, and you can write it in. So to write it in, you have to again select a process. If you have multiple processes, it gives you an option to select which one you like. And then you basically inject into it. Now, this was written in a kind of modular format in the hope that if someone would like to bring in new injection techniques, they can just add them in right here. So this is what I have for now. The classic create remote thread is what I use, but you can use hollowing, herpaderping, what you'd like. You select the process, you inject the DLL in. So now what's happened is we created a modified DLL that has the shareable property, and we forcibly injected it into our target process, but nothing else as of now. So once that's done, you can even erase it. We will get to that soon. And you execute the return payload with create remote thread. Sorry if that seemed like a blur, because the demo or the fake demo will be looking like this. So once you execute the command, one of the first things I tried was your classic calc popper. Now I'd like to particularly show you what happened. Now I targeted this notepad process right here, but if you notice, a ghost kind of notepad process also spawned up. Now what happened here is, usually if you think of shellcode, if this is the legit code and you insert your shellcode in, what happens is it goes through the code and then it's some random code there and it'll cause your program to crash. It's very unlikely that it'll be perfectly aligned to get some decent or legitimate bit of code. It'll be just random gibberish at that point. So what I've been able to do is add something called a return code stub, which may have been missed while I've been showing you. Yeah, it's all right. Yeah, so what it essentially does is it finds the entry point or the main function of this process, adds a jump instruction at the end of the payload, so that once you're done with the code, it calls that function again. So this is interesting in Windows 10, because instead of keeping the original process, it just spawned a ghost process entirely, and then the calc popper. But you cannot see it in a process tree, it just looks pretty legit. This was my test bed. I tested it on a variety of platforms. It doesn't work on any of the older ones, just up to Windows 10. The property I noted of the new Notepad instance is also noted. But there's absolutely no difference on a bare metal machine and a virtualized instance. Now, two very specific use cases, which I will be taking a bit more time to explain. First is forensic evasion. So the state right now, we've created the DLL, which has the shared property set in. The target process has been loaded with the DLL as well. And we're going to write it and use a Yara scanner to check if we erase it on the point, will it still continue to be picked up by the Yara scanner? So, typical scenario, you have my malicious process here. I have the notepad process loaded with the fake DLL, and the code's right there because we've written it. This is the Yara scanner I built up. It's very simple. It's basically checking for strings such as calc or create process and the hex equivalents. So now, if you notice, this is a notepad process, and that's its memory footprint. And if you notice, the Yara scanner managed to find all of them. Now this is at the point where we've just hit write payload. And obviously, if you remember, I talked about something called erase payload. What it essentially does, it keeps a cache of the data it has replaced and replaces that old cache of data, of legit data again. So now remember, we are not interacting directly with the target notepad process at all. We are just changing it on the memory mapped in our DLL within our process memory space. And when you do that, the Yara file does not manage to match it again. So forensic evasion as one post-exploitation application. Second one is a bit more interesting. It's privilege escalation. So I have a dummy admin process which is privileged, and my malicious process is going to be running unprivileged. It will still create the DLL, but the privileged admin process is going to load it from a fixed path. And there is no user called Boku at the moment on the system, but we're going to see what happens. So this is my dummy code. As you can see, it just references a hard-coded DLL path without any other checks. And once it does that, it specifically calls a function called amc-initialize, as you can see. And this is what we're going to leverage with the specific function targeting functionality. So if you notice here, this is the dummy admin process. It's elevated, while my process is not elevated. And if you get back, the memory is written, it's all there. And if you notice at the moment, if you use a net user, these are the only users that are there. There isn't a Boku user yet. And once you run the execute payload option, now you do not run the execute payload unlike the previous one, because this code is capable of directly calling the amc-initialize. We just patch the amc-initialize function over there. It's only and this privileged function will automatically call it next. The moment you execute that, suddenly a Boku user is added, and they are also added to the administrators and remote desktop users group. And that is my story of how I built that tool, which does hopefully a bit of post-exploitation. Thank you.